So let's derive the time period of a simple pendulum. So suppose this is your rigid support and this is a massless string and this is the bob, and suppose this is the vertical axis, and suppose this pendulum makes an angle theta with respect to this vertical axis. So what all we require to prove to find the time period of this simple pendulum? Well, let me write it. Let me draw the line first of all. Right? Okay. So first of all, we will be needing energy conservation. Energy conservation, right? Okay. Second, we will be needing cos theta is equal to 1 minus theta square by 2 factorial if theta is very small. And this directly comes from the Taylor series of cos theta, which is equal to 1 minus theta square by 2 factorial plus theta raised to the power 4 divided 4 factorial and so on and so forth. So if theta is very small, then theta raised to the power 4, theta raised to the power 6 will be very small value. So they are negligible over here, right? So that is why cos theta is equal to this quantity. And third, we'll be needing that the velocity at any instant is given as v is equal to L omega, where L is the length of this simple pendulum, correct? And of course this length is from this point to the center of mass, right? Okay. And we can write omega as d theta divided by dt, right? Okay. So v is equal to L d theta by dt, correct? Now why we have v is equal to L omega? Well, if you remember in the circular motion, velocity is given by v is equal to r omega, right? So this is also circular motion because the length, the locus will be like that only if you find its locus, right? The points, whatever be its trajectory, suppose like this it will be like this, the trajectory will be there, right? Hence this path is like a sector of a circle, right? With the angle varying from 0 to maximum some theta, which is maximum. Okay, so like that. Hence velocity is given like this, correct? So now let's apply energy conservation first of all, right? So suppose we have to make one more assumption over here. Suppose this is a point A, and suppose there is a point like this, and here we have the bob, and this theta is the maximum theta naught, and this is a random theta, correct? So over here velocity will be 0, right? And not the elongation, the amplitude will be maximum, angular amplitude. Okay, so we can conserve the energy at A and B. So energy at A must be equal to energy at B. No need to write 1 and 2. Okay, so E at A is equal to E at B. So what is energy at A? It is equal to half mv square plus mg h1 is equal to mg h2, right? Because of course there is no velocity at point B, correct? Okay, so how we find the these h1 and h2, right? So let me give you a very simple example, right? This is the vertical axis and this is the bob, and this is the horizontal plane over here. So earlier the bob was over here, right? Okay, it went from here to here, right? So suppose this is the mean position and this is the extreme position, correct? Or maybe some random position. Okay, so at theta, so it has moved an angular displacement of theta, correct? So earlier this, of course this length won't change, so this so the component of this length will be L cos theta, and what is the total length? It was L. So the height is what? This expression L minus L cos theta, right? So H is given as L minus L cos theta, correct? So from there we can say that h1 I can write over here. H1 is L minus L cos theta, and H2 is L minus L into cos theta naught. Correct? Okay. So I have half mv square plus mgl 1 minus cos theta is equal to mgl 1 minus cos theta naught, right? So we have half mv square. If you solve it further, you will get it as mgl times the quantity cos theta minus cos theta naught. Correct? Okay. So mass and mass will get cancelled, and you will be left with velocity is equal to square root of 2gl of the quantity cos theta minus cos 2 theta. Correct? Okay. Correct. So you got the expression for velocity at an instant with respect to theta. Okay. Now for very small oscillation, that is for very small theta, cos theta will be equal to 1 minus theta square by 2 factorial, that is 1 minus theta square by 2. Correct. So velocity can be written as square root of 2gl times the quantity 1 minus theta square divided 2 factorial minus 1 minus 1 minus theta naught square by 2 factorial, and if you evaluate it you will get square root of gl into theta naught square minus theta square. Correct? Okay. And of course theta is in radians. If you don't know, theta is in radians. Okay. So now I will apply the formula v is equal to L omega, that is L d theta by dt. So L, or small l I should write, else you will get confused. L d theta by dt is equal to what? It is equal to square root of gl theta naught square minus theta square. Correct? Okay. Now clearly I can rearrange this, and I will get d theta by dt is equal to square root of g by L times the quantity theta naught square minus theta square. Correct? Okay, so let me erase this stuff and then we will solve this expression. So clearly we can separate theta and t, right? So we have variable separation methods. D theta by square root of theta naught square minus theta square is equal to the quantity dt, or first of all let me write the constant d g by dl dt, right? Okay. Now just integrate this stuff. Now what we have to take the limits. Let me tell you. Okay. So suppose this was the surface. Okay. So sorry. So suppose it is the pendulum over here. Correct. Suppose this is at mean position, right? So it will have some velocity. Suppose in this direction, right? Correct. So suppose it goes to some maximum value over here at theta naught. So suppose in this process it takes a time of t, suppose tau, right? Now tau should be equal to total time period divided by 4. Why? Because if it's going like this, so it will take 1/4 of the total time period to move in counterclockwise direction. Then when its velocity will become 0, then it will start moving in clockwise direction. It will come to the main position. It will again, in that process, it will take t by 4 again. So t by 4 plus t by 4, which is equal to t by 2. And when it will reach its mean position, its velocity will be along this direction then, and it will keep on moving in clockwise direction. And once its velocity becomes 0 here, it will again start moving counterclockwise direction. Correct? So it means t by 4 and t by 4 and t by 4 and t by 4. So total time period becomes t, right? So we want that only. So that is why tau is equal to t by 4. Okay. So when it is at mean position, it is of course t is equal to 0. Correct? So at that point theta is equal to 0. Clearly we can see. And when t is equal to t by 4, we have theta is equal to theta naught. Correct? And now we have to just evaluate this integral. So let's see how we will evaluate this. Okay. So after that you have said this kind of integral, let me prove it also that how it looks. Integral of the quantity 0 to integral of this function d theta divided by square root theta naught square minus theta square, correct? So let's assume theta as some theta naught into sine of t, correct? You all must be knowing such kind of substitutions. So d theta is equal to theta naught into cos t dt, correct? Okay. So the integral will be from when theta is equal to 0, sine t is equal to 0, that is t is equal to 0. When theta is equal to theta naught, then sine t is pi by 2, correct? So we will be getting over here d theta as theta naught into cos t dt divided by the quantity is square root of theta naught square minus theta naught minus theta square. So theta is equal to theta naught into sine t. So what is theta naught square minus theta naught square into sine square t? It will be equal to the modulus of theta square theta naught into cos t, right? Now notice that in 0 to pi by 2 limit, this will be always positive, right? Okay. Hence, this will get cancelled with this quantity, right? So we are left with integral 0 to pi by 2 dt, which is equal to pi by 2, correct? So this integral is equal to pi by 2. So pi by 2 is equal to root g by l into t by 4. So clearly we can say t is equal to 2 pi root L by G, and that's the answer. Now there was a step which I used there, that for very small angle we had this expression. So using that expression only you can derive a general formula for time period of a simple pendulum, because of course if the amplitude, the angular displacement is too long, or like very big, more than 10 degrees or 20 degrees, then clearly then also there will be oscillation, just it won't be SHM, right? So to calculate the time period in case of higher angles, that is when theta is not small, it is large enough. So for that I'll make another video. Till then, bye bye, take care.